Welcome to the course on smart materials and intelligent system design. This is a MHRD sponsored MOOC course in which we will be talking about the realm of smart materials and how to build up intelligent systems using smart materials. So, in this particular course, we will be following these following books: Smart Structures Theory by Indrajit Chopra and Jayant Sirohi, which is from Cambridge Press, and also Smart Material Systems and MEMS, Design and Development Methodologies by V. K. Varadan, K. J. Vinay and S. Gopalakrishnan, which is from John Whaley and Sons. Both the books will be required for different parts of the course, which I will be explaining, and at these particular places wherever it will be required, I will mention that which textbook will be relevant to you. Now, this is what is the course plan in terms of how we will run the assignments. We will be having one assignment per week. So, total there will be 4 assignments. Final score will be calculated on the basis of 25% of this assignment score plus 75% of the final score, which is optional. Now, 25% assignment score will be calculated based on 3 out of 4 assignments, best 3 out of 4 assignments, and the final score will be evaluated for those who will opt for the final exam. We will issue the e-certificate for those who will register and write the exam and whose score will be greater than or equal to 40% of the final score. So, I encourage all of you to register for the course and also to get a certificate for the course, because that will be important for you for future activities in this very important area. Now, the course content also, let me talk very briefly about it, that in this particular course I have divided it into 6 sections. In the first section, we will talk about the overview of smart materials, in which I will talk about various very commonly used smart materials like piezoelectric materials, magnetostrictive materials, shape memory alloys, electroactive polymers, etc. So, we will get first an overview of all these materials. Next, I will be going to composite materials. The reason being, whenever you will be developing intelligent devices, you have to embed these smart materials into composites. So, you have to know what is a composite, how a composite is made, and what are the basic governing equations of analyzing a composite system. So, that is why I will first give you an introduction to composite materials, and I will talk about the mechanics of composite materials. Now, once we have a fair idea about these two topics, then we will apply our knowledge of smart materials in terms of the modeling of smart materials. So, then you will see that how the constitutive relationships of smart materials can seamlessly go inside the mechanics of a composite system. Now, once we have gained the experiences in these first 4 topics, then we will go into the building up of intelligent devices. To do that, our first step will be to talk about actuators and sensors, which are based on HBLS, which is high band low strain smart materials. So, smart materials are generally categorized into 2 groups. One is a high band low strain and another is low band high strain. So, what we mean by high band low strain is that for high bandwidth, it has a high range of frequency, particularly it can go up to gigahertz range, which means as sensor or as actuator it will be a very, very fast system. On the other hand, low strain signifies that as actuator the deformation that will happen to the system will be low, but you can exploit it, as I will be explaining later, in terms of large forces. And there are some other group of smart materials which are of low band, that means they are range of frequency available is smaller, but they can give you high strain. Some of the examples are shape memory alloys and electroactive polymeric materials, like again polymeric shape memory alloys, SMPs we call it, shape memory polymers. So, I will talk about them additionally when we will first talk about HVLS, after that I will just briefly discuss about it. Next we will come to the concluding part, which is intelligent devices based on smart materials. So, how to actually develop intelligent devices using these smart materials. So, this is what will be the course content, and in the first week we will first focus on overview of the smart materials. So, let us begin with the introduction of the smart materials. What we will be talking about in this lecture is, first of all, what is a smart material, and then we will talk about the applications of smart material and how can you build up smart systems using smart material. We will also talk about little bit about smart actuators, and if time permits about direct and reverse effects. So, the first question is that this very fundamental to this particular course is, what is a smart material or what is not a smart material. There are certain telltale features of a smart material. First of all, smart materials belong to a group of materials which is broadly known as functional materials. Okay. So, the term is slightly misnomer. Does that mean that materials are generally not they do not function? Well, it is not exactly like that. What it means is that generally materials are unifunctional. For example, when we explore a particular material, we look for some unifunction, unifunction like say for example, strength. So, that is one of the important thing in mechanical engineering, that we search for materials which gives us high strength. Okay. Then similarly, we can choose materials which gives us a conductivity, be it electrical conductivity, be it thermal conductivity. We can choose materials for that. We can choose materials which can give us hardness. We can choose materials which can actually give us certain electrical properties. Say for example, you can use them as a capacitor or you can use them as inductor. We can also search for materials which can give us a certain magnetic effect or electromagnetisms, etc. Now, each one of them are unifunction, but if some of these mechanical properties get actually coupled with some of these electronic properties, then what we get are actually functional materials. And smart materials indeed have this kind of coupling between mechanical and electronics properties of a material. The other way to look at it is that, what are the energy forms that gets interchanged in such materials, because in every material, whenever we apply say for example, a mechanical force to the system, then the force, many things can happen, but the major part of the force may go to deform the material, which means the energy will be stored inside the material in the form of strain energy, which is a mechanical energy. But suppose the material gets heated, then that interchange is in terms of thermal energy. Suppose it also generates voltage, then that mechanical energy gets interchanged to electric energy. Suppose it generates a magnetic field, magnetic energy, sound energy of course, and vice versa from electrical energy to mechanical energy. So, all these interchanges, if a material allows, not every material would allow such a thing. We would later on see that certain crystal structure only promotes this kind of interchanges of energy. So, that is another telltale sign of a smart material. Then the other interesting feature is that these materials can be actually designed in a manner that they become adaptive, they become cellular in function, self sensing, they can sense and they can actuate on their own and they can control themselves. All these properties I will unfold as will be discussed about smart materials, but very briefly what adaptivity means is that as the environment changes, can the material change its behavior based on the environment. Like I will show you a particular material which as the temperature changes its stiffness, which is known as shape memory alloys. The cellularity in function actually means that just like biological systems where every cell works in a kind of an autonomous way, you can store them and you can keep them alive even if you can detach them from a particular living system for some time. So, that is the capacity that every cell has a degree of autonomy. Similar to that, whenever we will be having a smart device, you will see that every smart material unit in it, because it is these powers are derived from the atomic structure or from the molecular arrangement. So, at a very small scale level they are actually cellular in nature. So, that is why they are analogous to biological materials. And finally, which is why I will be talking about composites as soon as we will talk about smart materials, that these materials the moment you put it inside another structure, it becomes a composite structure, and that is the capacity of these materials, they are highly embeddable. So, in a nutshell, that if a material belongs to the functional group, if a material has the capacity to interchange the energy, if it is kind of adaptive and cellular in terms of its nature, and if it is highly embeddable, we can say that yes, these are the features that makes the smart material. So, when we say smart, so that means there must be a scale in terms of the smartness. Now, what happens if something is not smart at all? Okay, so, the way we colloquially say if somebody or something is not, we say that stupid, and maybe a little better than stupid as per dictionary is dumb, or maybe little better is foolish, little better is trivial, little better is sensible. Now, the degree of smartness starts from the sensible point onwards. That means, it is smart or clever. Even if it is better than smart or clever, then it will be intelligent, and if it goes beyond the common level of intelligence that occurs, which is what is the future of all these materials, is that can the materials themselves or the systems that we can build using the material be wise. So, which is a distant future that if it can happen in reality. But this is what is the direction in which we are trying to develop materials which becomes more and more and more intelligent. Now, present smart materials are actually in the range of highly sensible to maybe poorly intelligent level. Okay, that is the range in which our smart materials are currently placed. Now, this kind of highly sensible to poorly intelligence, how do we range them? How do we say that a particular smart system is highly sensible, or a particular smart system is more than sensible, it is smart or it is intelligent, etc. It actually starts from passive smartness to get a highly sensible material. By passive smartness, what we mean is that it has a limited capacity to deal with the change of environment, but that capacity also is actually prejudged. You cannot really change that capacity as the environment suddenly changes. So, that is like our passive smartness. One of the examples that I always give is the multi-phase rocket nozzles of space shuttle. If you look at a space shuttle, you will see that the structure of a space shuttle is a very complicated system. It has actually multiple levels of materials in it. It starts with porous tungsten with silver coating, it has graphite, it has ceramic layer and it has steel. So, each one of them are actually meant for certain particular function, like the porous tungsten with silver coating gives it high temperature, as well as because it is porous, the tungsten, it gives less thermal stress concentration in the system. If I add graphite to it, I get higher temperature resistance. If I add ceramic layer to it, I get even higher temperature resistance, because the tip of these particular space shuttle is subjected to something like close to 1500 to 1600 degrees centigrade of temperature. So, you need to have these three systems fighting these high temperature. As the temperature increases more and more, the porous tungstens, graphite and all these layers, they actually help in terms of resisting this high temperature. But inside, deep inside, what you have is steel, which is needed for actually, because steel is machinable. So, all the equipments that you will be having inside the system, the steel part actually helps in terms of joining them with the structure. So, that is why it is needed. So, this is a sensible design, where you have thought of that as a space shuttle is going or it is coming back to earth, what is the different level of temperature pressure that it will be undergoing, and you have designed a structure beforehand thinking of all these various possibilities. However, the problem is that this is an open loop structure. What if my space shuttle does not enter earth? What if by chance it has to be targeted to moon or some other planet? Then this system may not work, because this system is precisely designed for the for leaving earth and for re-entry in the earth based system. So, then in such cases the passive smartness fails. You need some kind of an adaptiveness in the system. So, passive smartness lack the inherent capacity to transduce the energy, because it can only convert the energy to a particular form. It can act only generally as sensors, but not as actuator, and so you need an active system. Another example of a passive system is this optical fiber cable. If you ever see these TV cables, if you actually cut these cables, you will see that it has several layers. It has a core layer which is actually transmitting the optical signal, then it has a cladding which actually helps the signal to remain inside the core itself. The refractive index is designed in such a manner. Then it has a buffer coating which actually helps this system to not to get exposed to the ambient weather, etc. So, once again this is designed considering a particular range of temperature, pressures, etc. What if these things changes? Then the optical fiber has to get that kind of an adaptiveness into it. So, this is what is the smartness in a scale of intelligence that we are looking for, that can we make it more adaptive, like an active smartness. Now, when we talk about active smartness, we talk about a material which possesses the capacity to modify either their geometry or their material property. So, and it definitely, as I told you earlier, that it must have the inherent capacity to transduce the energy. Now, if you look at it, that if you get these properties, then you can actually design it a manner that it can be acting both as sensor or as well as actuators. Let us give some examples. One example is this piezoelectric material. I will talk about all these materials later on, but let us first of all take the names with us, that there is a group of material called piezoelectric material. If I apply mechanical stress, so this stress is mechanical in nature. So, if I apply mechanical stress in this material, then I am going to get electric charge as well as the mechanical strain. Again, if I apply electric field to the material, I will be getting electric charge as well as mechanical strain. So, which means I can use this material in terms of either using electric field I can generate mechanical strain, then it will be working as an actuator, or I can use mechanical stress and I can find out what is the electric charge that is generated, then we will be using it as a sensor. So, you can use it both as actuator as well as sensor. There are other materials which cannot be used as both sensors and actuators, like shape memory alloy. If you look at it, if you apply heat, there will be a geometry change in the system. So, that geometry change can be actually used in terms of generating mechanical forces. So, in this case you are using a non-mechanical input and you are getting a mechanical output from the system. This kind of things can be used in terms of then building it as an actuator. Again, in another case you can actually change the material property, not the geometric property, like if you consider the electro-rheological fluids. If you apply electric field as an input, you will see that the viscosity of the system changes. So, there is a change in viscosity and that will change the internal dampings, etc. So, this is very much used in terms of what you call suspension system designs in mechanical systems. If you use magnetic field as an input, then there are materials which are known as magnetostrictive materials. They transduce and they actually generate the mechanical strains. So, this is another group of material with another capability of transduction of energy. So, there are like that the many other transductions that we will be actually summing up in a matrix soon. So, you will see that what are the other possibilities that is there. So, let us have a brief comparison at this moment between a traditional system and a smart system. As exactly we have discussed earlier, that traditional systems are designed for a particular performance requirement in terms of load, speed or lifespan. They are unable to modify their specifications if there is a change of environment. On the other hand, smart systems can accommodate unpredictable environment. They can meet this performance requirement of course, and they offer more efficient solution for a wide range of applications. That is why they are so popular today. If I try to now define that what smart materials are those which possess the ability to change their physical properties in a specific manner in response to specific stimulus input. So, this is important that they are able to change their physical properties in response to specific stimulus input. Like I told you that piezoelectric material is one such smart material which can actually generate an electric charge in response to applied mechanical stress, and also it can actually generate mechanical strain in response to the application of electric field. Let us look at an example of how you can use this technology. So, if you look at all of you must be acquainted with a printer. So, how does a printer work? If you look at that, what you will see is that the printer basic technology is actually based on smart material. There is a piezo element in each printer which if I apply voltage to it, it expands or contracts, or you can also by adding an inert material you can also bend it to whatever direction you wish. Now, you see that you are bending and as a result it is giving pressure, as a result you are controlling the fluid flow. If there are thousands of them, that is what it is there in any printer, they are controlling the fluid flow essentially of various colors. Now, you see they are controlling these fluid colors, and that is what is arranging themselves in an array, and all these arrays in their layers together is actually giving you a particular print that will come up. So, essentially you can see that in any common printer, this is what is the technology behind the printer, that it essentially uses piezoelectric material to implement this kind of a printer operation. Now, if you look at another smart material which is called magnetostrictive material, it has actually change in dimension it happens mostly in ferromagnetic materials due to magnetic field and vice versa. So, there are some ferromagnetic material and there are in fact some materials where this effect is too prominent actually. So, these are magnetostrictive materials where the magnetic field can affect this change. So, the last change that we have seen in piezoelectric material, there the change is happening by the application of electric voltage, whereas here it is by the application of magnetic field. There are some materials like phase transition dependent materials like shape memory alloys, they can actually remember their original shape and after being deformed they would return to their original shape. I will show you in this course sometime that how in our laboratory we use this shape memory material for actuating different systems. Now, there is another material which is electromagnetorheological material I told you, which actually changes its viscosity in response to electric or magnetic field, like as you can see in this particular case, that if this electric field is not applied, the fluid is flowing. If the electric field is applied, it becomes so viscous that it does not flow. So, the idea is that if I can make almost like say a super viscous material is what? It is like glass. So, if I can make a material super viscous, it will behave almost like a solid material. In that case, it will be able to transfer mechanical forces like a clutch system, if you think of it, that it will work like that it will be able to transfer the mechanical power. But if I withdraw the electrical energy, then it will become once again fluidic, and that means it will be isolated. The two systems which is joined by it can be suitably isolated by this particular way. So, these are various examples of the smart material. So, why are we so keen on studying these smart materials? Because you can make sensors and actuators out of them. And what is so important about such sensors and actuators? A, they are very fast. So, you get real time response, that means there is no delay. You put the material, immediately you will start to get the response of the system. You can exploit various functional properties of the material by using this. It is embeddable also. So, you can put it into a structure very nicely, so that you are not attaching something ad hoc externally. It gets very seamlessly integrated into a system. It has minimal effect on structural properties. So, it has reasonably good structural properties on its own, and in fact, many of them are light. So, quite light. So, there you get a reduction in weight, and if you compare them with a traditional system, there will be much less power consumption, and it has a much better reliability as a system. So, if I actually look at a range of applications, some of them are laboratory based, some of them are actually already commercially available, like the first example, which is an isolator, which is used for space applications. This is where a smart material is used. Also, energy generator, this is where a smart material is used. These are commercially available. Some other technologies we are developing in laboratories, like this finger, whatever it is doing, the robotic finger is trying to simulate it. So, we call it as a master to slave training, and that is possible because of the smart materials that are there, which are actually sensing the change of strain, communicating it to the system, and thus you are getting exactly the slave performing the same way. This is something which we feel will be very useful for telesurgeries. Then also there is something like you may be able to follow that there is a wing here. So, this wing, which is like a butterfly wing, if I apply an electric field, the wing can actually flap. So, you can actually develop an insect which can actually flap, and as the insect can flap, then you can actually use it for various surveillance activities, etc. So, there are a range of such applications possible. Now, here comes the very important table for us, okay, that this table will also tell us that which materials are smart and which are not. So, if we look at it, that we have the outputs and inputs. This is the way the table is arranged. In the input, we have considered electric field, magnetic field, stress means mechanical stress, heat and light. In the output, we have considered current or charge, magnetic field corresponding to that magnetization, mechanical stress corresponding to that strain, heat corresponding to that temperature and light corresponding to it, light itself. Now, if I look at the diagonals of this particular matrix, if I look at it, then if I apply electric field and I actually get current out of it, then it is the conductivity that is operational. If it is a dielectric material, I get charge out of it. So, that is due to the permittivity. Now, that is not smartness, whereas if I apply electric field and I get a mechanical strain which happens due to reverse piezoelectricity. So, any material can be either conductive or insulating in nature, that is not smartness, but if in addition to this conductivity or insulation, if the material can generate mechanical strain when I am applying electric field, then it is a smart material. Similarly, when I am applying magnetic field, if this happens along this column, the mechanical strain which is also defined by the Joule effect, then it is smart material. For heat, if there is a thermal expansion related to phase transition, not a normal thing, but a phase transition, then it is a smart material. For light, if the light itself changes the shape, then it is photostriction, it is a smart material. So, this column and so true is from the other side also, if I look at it, because this column we will get when we will take the mechanical stress in mind. If I take the mechanical strain in mind, then that coupling, if I look at it, like if electric field related and stress generating direct piezoelectric effect coupling, and again the magnetic field generating the Villari effect, and again temperature, thermomechanical effect and light, the photoelastic effect, then that is also another set in which we get this kind of a coupling in the smart materials. So, we can subdivide such smart materials into two groups. One group in which mechanical stress creates the electric potential. So, this is the direct effect, stress creating electric potential. The other group, so naturally this direct effect is used for sensors. The other group where electric, magnetic and thermal stimulus is giving me mechanical strain, this is what is there in the reverse effect or as actuator. So, direct effect is used for sensing and reverse effect is used for actuation purpose. What are the materials which shows direct effect? Well, all piezoelectric materials and PVDF, magnetostrictive materials and optical fibers, they all show this direct effect. That means, if I apply mechanical stress, I will get a change in electric field potential. So, we can use such systems for sensing. The reverse effect, where we are using a electric or magnetic field or a thermal stimulus to get a mechanical field, so that mechanical strain, so that you can use it an actuator. There are many materials, of course, all piezoelectric materials like ferroelectric perovskites is a very special structure. I will talk about it in one of the lectures. Piezoceramics, PVDFs, they all respond to electric field. Then there are group of materials like terphenol D, amorphous made glass, they show similar effect in magnetic field. Shape memory alloys show the effect in thermal field, and electromagnetorheological fluids respond to electric magnetic field by changing its viscosity. So, these are all categorized in the reverse effect. If I compare between the traditional versus new actuators, we will see that in comparison to the traditional actuators like air pressure, oil pressure or electricity, if you look at the smart materials, you will see that they have generally lower strain ranges etc., but they have much higher accuracies. Compare them with the accuracies here, okay, or accuracies here, much higher accuracies and also much faster response time. That is what makes smart materials to be so special in comparison to other materials. we can classify them in terms of the input parameters, like if the input is electric field, then you have piezoelectric materials, MEMS or ER fluid. If it is magnetic field, magnetostrictive material or magnetorheological fluid, chemical, mechanochemical effects, heat, shape memory alloys, shape memory polymer. If it is light, it is like photo strictive materials. If I go for various properties of these materials, one important property is how much strain is happening to it. So, this is known as free strain. There is no other force, just you are allowing it to get deformed. Now, then piezoelectric materials, this is PZT is a piezoelectric material that shows about 1000 parts per million, which is quite good in the piezoelectric range, PVDF little less. Terphenol D, this is a magnetostrictive material, I will talk about it. This shows actually more mechanical strain, that is about 2000 parts per million, and nitinol, this is a shape memory alloy. So, we call it SMA shortly, this shows maximum strain. Elastic modulus wise, all of them are quite good, except this PVDF, which is little low. An interesting thing to note is shape memory alloy has actually two different elastic modulus, it happens due to phase transition. Bandwidth wise, piezoelectric material and PVDF, they have the highest bandwidth, terphenol D has the lower bandwidth, and the lowest bandwidth is this particular SMA, which we call as low band high strain material, and these materials generally are categorized as high band low strain material. So, this is a broad overview of these smart materials. In the next lecture, we will talk about piezoelectric materials and their constitutive equations, piezoelectric polymers and composites. Thank you.